Hello, this is Chuck Ridgway. It's Tuesday and time for another technical topic. Now, for those of you who have perused our YouTube channel, maybe checking out the different videos that we've recorded for you over the past couple of years, you may have noticed that some of the more popular videos in terms of views are those dealing with communications. Now, it could be because people just want to learn about communications. It could be there's lots of confusion about which protocols you should use when. But whatever the reason, communications are popular. And as you can imagine, today we are going to be covering a communications video. Our topic today is using Modbus TCP for OCS-to-OCS communications. Now, Modbus TCP is certainly a protocol which we've covered on this channel many times before, but we've never really covered this aspect or this application of Modbus TCP, using it in those applications where you have multiple OCS controllers. And those applications are more common than you think. Maybe it's a situation where you're breaking up the control task into multiple pieces and having a different controller control each piece and then having them coordinate. Or maybe it's a case where you just want multiple screens on a machine, and using multiple OCSs is one of the ways to do that. Whatever the reason, that's our topic for today. Now, for those of you watching live, the advantage of watching live is that you know there's somebody standing by to answer your questions immediately in the chat section. If you're watching this on replay, give us your questions. Just do it in the comment section, and we'll go ahead and get those answered as quickly as we can. All right, let's dive into our topic. Using Modbus TCP for OCS-to-OCS communications. Here's how we're breaking it down today. We're going to do a quick review of Modbus TCP. Don't worry, we're not going to belabor the topic. We're not going to spend too much time on review, but for those who could use a little bit of a refresher, we're going to give it to them. We're going to talk about example applications using multiple OCSs. Where not to use Modbus TCP, because that's just as important sometimes as where to use it, and then of course where Modbus TCP can work well. Then we're going to give you some example workflows and give you multiple demonstrations. All right, here's our quick review of Modbus TCP. Well, as most of you know, it's the most common industrial protocol for the exchange of data between devices from multiple manufacturers. It's a client-server poll response protocol. That means typically you have a client which is polling a server or multiple servers and sending them queries, and they're getting responses back. Now, from an OCS standpoint, an OCS can be a Modbus TCP client, a Modbus TCP server, or both. Now, in Modbus, whether you're talking standard Modbus or Modbus over Ethernet or Modbus TCP, data is modeled after a traditional register-based PLC. The only native data types are integer and Boolean. However, everybody has implemented other more complex data types like reals and double integers simply by concatenating multiple integer type registers together. And on the right there, we have a diagram showing the Modbus data model. Okay, now in terms of the OCS implementation of Modbus TCP server, where the OCS is sitting there waiting for a query from a client and responding when they're polled, in that implementation, the OCS uses a map of its local OCS native registers over to Modbus address space. And setting it up in the OCS side, at least server-wise, couldn't be simpler. It's a single checkbox because it's a native OCS protocol. So literally all you have to do is check a checkbox to support Modbus TCP server in the OCS. Now, the implementation of Modbus TCP client in the OCS, there's a little more involved there. That's because the OCS is the one doing the polling when it's acting as the client, and it's polling other servers in a round-robin fashion. Now, there's a couple different ways in the OCS that you can specify the specific Modbus data that you want to read and write. The first method is really the one that works the best most of the time, and that is creating a scan list. So in the OCS that's acting as the client, you create a list of all the servers and the data within the servers that you want to poll continuously on a read-write basis. So that is probably the way that works the best, or at least offers the highest performance typically. But you also have the option from the screen editor itself to go into an individual graphics object on the screen and directly map its data source, not from internal OCS memory, but from the external Modbus server. So you have the ability within each graphics object you put on the screen to determine whether its data comes locally from the OCS, from its local variable or local register, or remotely from the Modbus server directly. And in that scenario, you're going to be specifying the data in Modbus form. Except in that case where you have multiple OCSs talking to each other over Modbus, and in that case, whether you're talking about the scan list or whether you're talking about directly mapping into a graphics object, if it's OCS to OCS over Modbus, you never have to leave the native OCS register memory styles of R's, M's, and T's. You don't need to leave those to go into Modbus addresses. You can just stick with the OCS native data types. Okay, now let's start talking about example applications where you could use more than one OCS. Let's start with distributed control. Now that's an application in which you're going to be breaking up the control task in an application between multiple controllers. An example we've used before when we've talked about Ethernet Global Data, which is another Ethernet protocol. An example we've used before is our example I'm shown graphically there on the right, where we have an assembly line with individual assembly carts, each controlled by an XL4, and there are multiple carts. And in the case of the multiple carts, they're all being coordinated with a single coordinating unit, okay, which in this example on the screen there is an XL7. Now, in this case, you've got a lot of units that need to exchange data, and a pull response type protocol is not a great choice here. A protocol that supports multicast is much better. Multicast is a communication scheme where one device can send a single message that's received by multiple other units. And that architecture works a lot better in this example here. So this is one of those cases where you would not use Modbus TCP for an application that uses multiple OCSs. The next application I'm going to talk about is one that we've had lots of customers implement, and that is where they design modular equipment, or a machine that has maybe a main section and then modular expansion units that can be added. On the screen there, I'm showing the example of a machine where you can expand the number of filler modules by just adding additional modules, and each module, if you will, is controlled by an OCS. In this case on the screen, I'm showing an XL4. This is another application where a lot of the time you could run into the same situation as the assembly cart example, and that is where the number of controllers that need to communicate with each other, as well as the path of the data from controller to controller, might make using Modbus TCP not ideal. So again, this is a scenario where Ethernet Global Data might be a better choice. Now let's talk about an application where Modbus TCP does work well typically. And that is a scenario where you've got a machine or an application and you want to have multiple operator stations. In other words, even though you might have a single controller that's controlling the machine, it would be extremely convenient or even mandatory really to have multiple locations where the machine can be monitored or controlled. Okay, so that's the application we're talking about here. And in this case, Modbus TCP can absolutely be a great choice for a couple of reasons. First of all, when you're talking about operator interface, even if your response time or your data update rate on the screen approaches 1 second, that's still plenty responsive enough for an operator interface type application, even though the workflow I'm going to show you in a few minutes can do way, way better than once per second. Now, the other thing that makes Modbus a good choice, besides the fact that a slightly slower update rate is not a problem, and that is that Modbus data is inherently read-write. It's not one-directional, it's typically two-directional. Let me give you an example there of what I'm talking about. With Ethernet Global Data and some aspects of Ethernet IP even, you typically have data that's going to the network and data that's coming from the network when you're talking about the perspective of any particular controller. So that data going out and the data coming back in is literally separate variables. With Modbus TCP, you can read and write the same data to the same registers. So the same registers can be read and written by multiple controllers. So that makes it a really nice choice for this application. Now let's talk about the workflow, or how we would implement multiple operator stations in an application. And I want to talk about how we can do this a couple different ways, but let's just start with the basics. So in the application examples I'm giving you, one of the OCS controllers, even though there's multiple being used, one of the controllers is being used as the primary machine controller. So all the ladder logic to control the machine, as well as all the I/O control, is all being done from what we're calling the primary OCS controller in this application. The second or third OCS is actually acting strictly as a secondary user interface. So it's not actually performing any of the control or driving any of the I/O in the application. Okay, so that's literally what we're talking about here. Now, in our first approach in solving this application, I'm going to talk about the approach where you're going to use two different Cscape files, two different application files, to solve the application. One file running on the primary controller that's doing the control, and the other file running in the secondary controllers that are being used strictly as operator stations. All right, so this workflow works as follows. First, we're going to complete the application in the primary controller, just as if it was the only OCS in the application. We're going to design our screens, we're going to design our logic, we're going to control the I/O, everything we would normally do if we only had one OCS in the application. We're going to go into that primary controller's program and make sure it's configured as a Modbus TCP server, okay, sometimes thought of as a slave. There's only a checkbox we have to check to accomplish that, because all the screens, all the other OCSs that are going to be accessing the primary controller, they're the ones that are going to act as masters, or as clients for better nomenclature. Once we've done that, now we're ready to start working on the program that's running in the secondary OCS. We're going to start with that first program that we just finished. We're going to make a copy of it. We're going to give it a new name. So we're going to go in and we're going to wipe out any logic and any remote I/O configuration in that second program, because remember, that's all being handled by the first OCS. Next, we're going to go in and configure Modbus TCP in the secondary controller, but not as a server, but as a client. We're going to go in and select Modbus TCP client for the secondary device, and then in the list of servers that we're going to be talking to, we're going to make sure we add our primary controller's IP address in there as the server we're going to be communicating with, and we're going to select native addressing as the Modbus data style that we want to use for that particular server or that particular device. That's because we don't want to have to leave the OCS register types of R's, M's, and T's when we're configuring the communications. Why should we? We just have two OCSs talking to each other. Next, we're going to go into the scan list of the Modbus TCP client in the secondary controller and add the appropriate register ranges for reading and writing from the secondary controller to the primary controller. Now, if we happen to have more than two controllers in the application, a primary and a secondary, if we have multiple secondary controllers, they're all just going to use this secondary program that I just talked about. Okay. So enough discussion, if you will, of the workflow. Let's actually demonstrate that workflow. Let me go ahead and fire up Cscape and show you what we're talking about here. Okay, so what I have here is I have the actual application that's running in my primary controller. This is my handy dandy epoxy-matic example that I've used many times in the past, and a simulation, if you will, a very simple simulation of an epoxy machine. And in our application here, we're going to want to have multiple OCSs on an epoxy machine so that there are multiple stations for the operator to monitor and control our epoxy-matic. So I'm starting with the primary program here. I'm going to immediately save it under a different name, so I'm saving a copy of it. I'll go ahead and call this secondary. Okay, so now I'm dealing with a second program, but it's starting out at least identical to the first. All right, I'm going to go ahead and start by wiping out my logic because I don't need logic in this secondary controller. So I'm going to highlight all the logic in the main loop and hit delete by right-clicking. For these other main loop modules, the ones that aren't main, I can just right-click and delete them directly. I don't even have to copy all and delete individually. I can delete the routines themselves, but you're not allowed to delete the main routine. Okay, so now all my ladder logic is gone. Next, I would go in and wipe out any remote I/O configuration that I had in the system. And I'll just tell you that my Epoxymatic does not use any remote I/O, so that's a step I don't have to take in this particular case. Next, I'm going to take a look at my I/O usage. And I've been a good programmer here, and I have made sure that I have I/O names assigned to each of my variables. And I was also careful when I created and did the mapping when I created my variables. I was also careful to make sure that all the variables that were important for the user interface, all the ones I was going to need to be able to share between the two controllers, I made sure that those were more or less all in consecutive locations, and I went ahead and started those from register 1. So in this example application using register-based logic, I started all my word type data at register 1, and then all my bit type data, and I only had a couple of T bits or a few T bits, those all started at T1. So I've got a total of about 18 registers that I'm going to need to read and write between my two controllers, and I've got about 5 bits or so that I need to retrieve as well. Now, it wouldn't matter if you had a lot more data than this. The approach would be the same. Try and keep them as consecutive as you can so it's more efficient for the two controllers to exchange the data without having to do an excessive number of messages. Okay, so now I've got a good handle on the data that I need to exchange over Modbus TCP. Now I'm going to go ahead and go into my configuration and go to my LAN configuration and start making changes. Now, I'm not going to have the same program or the same IP address for my secondary controller, so I went ahead and changed the IP address. Now, I'm hard coding the IP addresses here. It's not always the best approach, but it's the approach I've taken for this particular example. The next example I show you, I've taken a different approach. So I made sure we had a unique IP address for my secondary OCS. I made sure Modbus slave, more correctly called Modbus client, was configured. And that's the step that was done for the primary controller. For the secondary controller, I don't want it to be a Modbus server. I want it to be a Modbus client. So I need to add it under downloadable protocols here, Modbus client. And there's 3 steps to the configuration process. Let's go through those. So on the network level, first of all, my timeouts, the default timeouts are way too long. For 2 OCSs talking to each other, 250 milliseconds is plenty of time to time out. So I'll change the number of retries from 1 to 2, and then reacquire time, I'll bump that way down as well to ½ a second. And I always want to make sure that I take advantage of status information when I'm doing communication. So I'll go ahead and assign the first of what will be 8 consecutive integers or 4 32-bit data values for monitoring the communications. Okay, so that's the network level for configuration. On the device level, this is where I need to tell my secondary OCS about the primary OCS that it's going to be talking to. Okay, so I'll give it a name. I'll call it primary. I'm going to, again, this isn't always the best approach, but I'm going to go ahead and hard code in the IP address of the primary controller. Okay, and down here under addressing style, this is where I'm going to select native addressing. Okay. That way, when I specify the data that I need to exchange between these two OCSs, I can use R, M, and T type addresses and not have to switch to Modbus address registers. Okay, and then again, I always want to enable. There we go. I always want to enable status information wherever possible, so I'll enable status on the server with two 16-bit words starting at R3009. Okay, so that is the device level configuration. Now I need to add or create a scan list. All right, so this is the specific data that I'm going to be reading and writing between myself, which right now I'm programming the secondary OCS, and the primary OCS doing control. So I will be reading and writing with that other OCS that's been selected for me. I'm going to go ahead and start reading at %R1, and I'm going to need to make sure I at least cover the first 18 registers, but I'm just going to go ahead and make that 32. So I'm going to read and write 32 registers. I need to make sure it's at least as big as what I absolutely have to have. So 18 is what I need. I'm going to go ahead and configure 32. So this is what I'm reading and writing from the other unit. And then locally, I'm just going to store it in the same location because I want all the memory locations to line up. I also want this to be a polled read-write. Okay? Now the reason I don't want it to be a polled read-write init, with a polled read-write init, what that means is that myself, as the Modbus TCP client, at PowerUp, if any of my data values vary from the server, I'm going to write those first and then read them back again at PowerUp. But in this case, I want to use the values from the server at PowerUp. I don't want to overwrite them. So I'm just going to select polled read-write. And then I'm going to do the same thing for my T bits. Now, if I also had M bits, I would do the same thing with M bits, but I don't have any M bits in this case. All right, just making sure everything lines up. I need at least 5. I went ahead and did 16. And we're good to go. All right, so for all intents and purposes, I am now done with the configuration of this secondary OCS. Okay, so that's really all it takes. And I'll go ahead and save the program here. All right, so what we did was we took the program running in the primary OCS. We deleted the ladder logic. We deleted any remote I/O configuration. We went in and checked to see which R's, M's, and T's we're going to need to exchange with the primary controller. We went in and configured Modbus TCP client in this particular program to make all that happen, and we're done. Okay, so hopefully you found that enlightening. All right, let's head back and talk about our next example. And our next example is that in which we're going to accomplish the same thing, except this time we're only going to use one program running in both units. Okay, so we don't have a separate program for the primary controller and the secondary controller. We're going to create a single program that both of them can execute, all right, so that we have one less program to maintain, right? That's always a benefit if you can do that. Now, I will talk about a caveat here, and that is this. If you are using remote I/O in the application, this approach I'm getting ready to show you probably won't work. And that's because you can't have both units configured for the same I/O, remote I/O at least, fighting over who's in control. Okay, so for the applications where there is remote I/O, this approach I'm showing you won't work. But in a lot of applications, there is no remote I/O. All the I/O is local, and so then it won't be a problem. So what's the approach we're going to take? Well, we're going to start out the way we started before, and that is configuring the application in the primary controller just as if it's the only controller. We're going to configure the logic, we're going to configure our screens, we're going to go ahead and configure our I/O and all that sort of thing. Okay. Next, because we have one program running in two different functional units, we're going to need to add to our program a flag that can be controlled from the screen at setup time to tell the unit whether it's acting as the primary controller in the application or whether it's acting as the secondary controller in the application. Okay, so that's something we didn't need before when we had a separate program for everything. Next, the example I'm showing you is going to be variable-based logic. Now you could do it in register-based logic, but I'm showing you how to do it in variable-based logic for this part of the example. Okay, so in variable-based logic, when we edit our variables, we use the program variable window. What we're going to do there is we are going to add a set of arrayed variables. One set of arrayed variables for M bits, another set of arrayed variables for T bits, and another set of arrayed variables for R bits. Remember, M's are retentive bits internal, T's are non-retentive bits internal, and R's are internal retentive word type variables. Okay, so we're going to create an array for each of those. And remember, I'm going to show you that here in a minute, so don't worry about trying to figure it all out just from the slides. Next, for all the variables that are being used by our operator interface functionality of our application, for those variables, remember, in variable-based advanced ladder, you don't have to go in and manually map M, T, R locations to your variables. Anything internal, you don't need to worry about that. However, in this case, for any variables that are on the screen that we're going to want to be able to control remotely with that secondary OCS, we're going to need to map those individual variables to particular M, T, and R bits so that they can be communicated outside of the unit. Okay, so this is one of those cases in variable-based advanced ladder where you actually do have to do some variable mapping. Not everything, just the variables that are basically communicated on the screen. Next, we're going to go in and enable both Modbus TCP server as well as Modbus TCP client. And that's because we have the same program being used by two units. One is going to act as a client, one is going to act as a server. Okay. Now, of course, the server configuration is checking a box. The client configuration, here's what we need to do. First of all, in Modbus TCP client, you have the ability to disable the protocol on the fly when you're a client. Okay, so we're going to use that primary flag we created as a bit that will allow us to disable Modbus TCP client if we happen to be the primary OCS. Because remember, in our application, the primary OCS is strictly acting as the server. Next, we're going to go ahead in our device configuration for Modbus TCP client, add our primary unit in, and set it for native addressing, just like we did in our first example. And then we're going to, in our scan list, we're going to use those arrayed variables we created for M's, T's, and R's. We're going to use those in our scan list for reading and writing data. One more step we have to take in this example that we didn't have to take in our first example, and that is this. We're not going to delete the ladder logic or the logic from our application because we need the same application to run in both controllers. So instead, what we're going to do is we're going to create a jump function that will allow the non-primary controller, the secondary controller, to effectively not execute any of the ladder logic. Next, we're going to take our newly created program, load it into both OCSs, and if we happen to have a third unit or a fourth unit, they could run the same program as well. Okay, and the second, third, and fourth units would be configured with the primary flag off. Okay, so now let's dive into our example. Let's head back to Cscape. So I'm going to go ahead and close this register-based program that I showed you before, and I'm going to fire up instead my program which is running in both my controllers and that has been based on variable-based advanced ladder instead of register-based advanced ladder. Other than that, it looks very much the same. From the standpoint of our logic, the logic looks the same, although of course you can see that there's no references to T's or R's or those sorts of things because of the fact we're using a variable-based advanced ladder. So the first thing we have to do is we have to add that primary flag from the screen somewhere so that somebody who's setting up the machine can configure each unit to either be the primary or the secondary. So what I've done in this case is I have created a new screen where not only can I set the primary flag here with this text table. So this is the primary screen flag that's tied to a text table, and what the operator is going to select between is primary controller and secondary controller, and I'll show you that on the screen here in a minute. Okay, so that's our flag. And then of course, because of the fact that each unit could potentially be used for either the primary or secondary, we have to have a way of configuring our own IP address as well as the IP address of the other screen that we're going to be talking to. So I had to add that as well. Next, let's go into the configuration, to the Ethernet configuration. Here's where I added a variable for setting the IP address. It's no longer hard-coded. Here's my checkbox for Modbus server, or more incorrectly called Modbus slave in our dialog box here. And then down here is where I've added Modbus client. Now let's take a look at what my configuration looks like. It looks very similar to what I showed you before in the register-based example. I upped my retries to 2, my timeouts, I bumped those way down to 250 milliseconds and a reacquired time of half a second. But here's the difference right here. My primary flag is being used as a disable bit. That means if I'm the primary controller running this application, I'm going to disable Modbus TCP client altogether. Okay? And then I've also, of course, added the ability to monitor status for Modbus TCP client. On the device level, again, similar to what we saw before, but this time the IP address is a variable and not hard-coded. We also selected native addressing, and we also decided to take advantage of status information. All right, this all looks pretty similar. And then in our scan list, okay, this is where we are using some arrayed variables, one tied to T bits, one tied to M bits, and one tied to R bits. So in the remote OCS controller that we're talking to, the one that is the primary controller in this case, we're going to be reading %T1 to 32 and copying it into this local arrayed variable that runs Modbus T sub 0 through sub 31. And we're going to use a polled read write. Okay, not a polled read write init, but a polled read write. And we're going to do that same thing for M's as well as R's. Okay? There we go. Now let's go take a look at our program variables so we can see the mapping that we have to do to make all this work. So here's our program variable list. Let's start with the global variables. Scroll all the way down here. All right, and we've got them by name, and here's where we have our arrayed variables for M's, R's, and T's. 32 M's, 64 R's, and 32 T's. Those are just the choices that I made, and then those were mapped to M1, R1, and T1. Okay, so that's the setup for the arrays that we need to make this all work. All right, the next step is to map the variables that we want to share through those arrays, through those addresses. We need to map our variables that are on the screen to individual locations, whether those are M's, R's, or T's. Okay, and you see that I've done that here. Now, I actually kind of went through, because this is a relatively small example, I kind of went through and just mapped everything. All right, I really didn't need to do that, but that's what I did anyway. All right, so again, you don't have to map everything, only the bit type variables and other type variables which are going to be available on the touchscreen. Let's do one more thing and then we'll show the live application. All right, I'm going to show you my screens one more time, okay, and just indicate that for instance, for the product select function here, where we're selecting which product we're going to mix, it's tied to an internal variable, and then that product select variable, just to look at that one variable, that product select variable, shouldn't have shut down my variable list, that product select variable, since it is on the screen, is one that I do need to, maybe it's under the global variables. There it is. There we go. So I did go ahead and map product select, which is an integer, to one of the specific R registers, which is inside my array. Okay, hopefully that was relatively clear what we're doing here. All right, next let's take a look at the application itself at runtime. So here is my primary controller. Here is my secondary controller. This one is doing all the machine control. So all the ladder logic is being executed here, and it's also acting to control the local I/O for the application, as well as acting as an operator interface. This unit is only acting as an operator interface. Okay, I just remembered one thing I forgot to show you. Let me head back to Cscape. The one thing I forgot to show you was that jump function to make sure that our secondary controller did not execute the ladder logic. Okay, now there's different ways this could be done, but what I chose to do is create a little section here, a little module at the very beginning of all the logic that basically says, if I'm the primary unit, so there's my primary flag, if I'm the primary unit, I'm going to execute a jump to jump to this section, which is basically the start of all my logic. If I'm not the primary unit, instead of doing the jump, I'm going to execute an end program. So that's how we can ensure that the secondary controller is not executing any of the logic in the application. Okay, now back to our actual application. So one thing you'll notice is if I make a change, say select a different product here, I'll select epoxy, I'll select the Adhesomatic, you'll see that over here, magically, that changes as well. If I change the size from quart to pint over here, you see it change over there. If I execute my batch, you can see, other than the fact that the flash isn't 100% synchronized, and that's not going to happen over a network, other than the fact that the flash isn't synchronized, everything is happening on both controllers. And that doesn't matter whether I do it where I operate from the primary controller or the secondary. I can do the same thing here as well. I'll switch to rocket rosin, all right, and I'll execute a batch of rocket rosin, instigating it from the remote unit, and everything worked beautifully. All right, now let's just, one last thing. Let's take a look at the configuration that needs to be done for each of these units to make this happen. So on our primary unit, we've configured its IP address, the IP address of the other unit it's talking to, and its role as the primary controller. Okay, when we press this button, we have our choice between primary controller and secondary screen. Okay, of course we want primary controller in this case. And then similarly, we're going to select the local IP address, the remote IP address, and the functionality of the remote unit as well. Okay, so that's our application. One last thing I want to show you, going back to Cscape, let's take a look at the status for the Modbus communications. So I'm going to go ahead and open up a status window that I saved here that's showing me the communications that's happening. All right, so this first status register is telling you how many milliseconds it's taking to read and write all the data. And you can see that worst case scenario, we're looking at about 40 milliseconds for the communications between these two units using Modbus TCP, using the scan list approach that I showed you here. Okay, so you can certainly, for a modest application, a small application really, do way, way, way better than 100 milliseconds even. And if you're efficient in the way that you map your variables, you can even accomplish probably sub 100 millisecond response even for a larger application. Certainly, you can keep it below 1 second. So hopefully that was enlightening. Let's go ahead and wrap up now. So the first thing we talked about was that pull response protocols like Modbus TCP aren't always the best choice for distributed control applications. If you need control type response times and communication times, 10 milliseconds, 50 milliseconds, 20 milliseconds, Modbus TCP for those sorts of multi-drop type communications in a pull response architecture, it's not always the best choice. Protocols that support multicast like Ethernet Global Data are better in those applications. However, Modbus TCP can be an excellent choice when you want to add additional screens to an application and you're primarily functioning, those second and third screens are primarily functioning as user interfaces. And there are multiple ways of solving the application, maybe using one program running in both controllers or separate programs for each controller. And we showed you those. One example using register-based advanced ladder, another variable using variable-based advanced ladder. So I do want to mention that if you haven't done so already, don't hesitate to subscribe to our channel. It doesn't cost anything, of course, and if you subscribe and choose notifications, you'll be notified every time we go live or every time we post a new video. Also, next week, we think we've got a good program for you, and that is comparing Ethernet IP, Modbus TCP, and Ethernet Global Data. Now, even though we've done individual programs on these particular protocols, we've never really taken a deep dive into the similarities and the differences between them. Okay? So that's what we're going to do next week. And remember, we're here every week, every Tuesday at 2 o'clock. If you have any questions and you're watching live, you can always chat them in. And if you're watching on replay, you can always give us the questions in the comment section and we'll answer them just as soon as we can. All right. Everybody, look forward to seeing you next week. And let's all get out there and do some good this week.